Hello everyone, myself Naman Khetan, and today I am gonna present this work for the framework of a multi-segment soft actuator design optimization. So the application of multi-segment soft actuator designs is actually immense, as we can mimic human fingers from them and animal claws. But despite recent advancements in the modeling techniques, the optimization techniques specifically for these multi-segmented soft actuator designs still remain challenging due to numerous parameters, added complexity, and the non-linear nature of soft materials. So we have tried to address this challenge through the application of a sequential lexicographic surrogate-assisted genetic algorithm for the modeling of a soft finger architecture. So first I will explain the algorithm architecture, then I will walk through the code, and at the end I will show the CAD and ANSYS simulations. So talking about algorithm architecture, it contains three key components: the inputs. So in the inputs, we have these genetic algorithm hyperparameters like initial population, number of generations, then the target configuration. So as I said that we are trying to mimic a soft finger, a human finger. So like in a human finger, there are like these MCP joint angle, PIP joint angle, and fingertip positions through which we can track their trajectory. We have these actuator and bone design parameters. Also, we have design constraints and material parameters. So like Young's modulus and Ludwig exponent. Now we are transferring these parameters to the Ludwig equation here. So like P here is denoting the pressure, Kn is the nonlinear constant, and theta is the bending angle of actuator. And N is this Ludwig exponent of the material which have been experimentally found for multiple materials. So here we are like using EcoFlex material. So with the help of this Ludwig equation and Latin hypercube sampling, we are creating a synthetic data set. Now this data set will be used for training of surrogate model. Here we come in the optimization stage, and we are training our surrogate model using radial basis function and this synthetic data set. And it is integrated with the sequential lexicographic genetic algorithm. Now, these are integrated as genetic algorithm explores through a wide space of design sets. And for each design set, we want to know the actuator bending angle. And this surrogate model here will help us to find that actuator bending angle as it is trained on this Ludwig equation. So the surrogate model here is acting like a quick evaluator. So we are also transferring these target configurations and actuator and bone design parameters in this genetic algorithm. And overall, this genetic algorithm has been divided into multiple stages. So as I said, this is a sequential optimization. So stage 1A involves actuator angle accuracy. We want to find, first of all, multiple design sets having minimal actuator angle error. Once we found those design sets, we will see that among those design sets which is giving us minimal energy. So we will select that specific design set giving us minimal energy, and as we want our design to be accurate and efficient too. Now we go to the stage 2A. So now we want to find the bone design parameter, and for that we are using the metric of end tip position error. Now this tip position error is being calculated using PCC analytic equations, and once we found out the multiple design sets giving us this minimal tip position error, we are applying the energy minimization function. Now in the outputs we are getting like actuator and bone design parameters, the angle error comparison across multiple target poses, the tip position error, and the fingertip trajectory comparison. So we will see all of this when I go through the code. So let's dive into that. So here like I have used these multiple installation files. So like NumPy, Pandas, Matplotlib, surrogate model. SMT toolbox has been used for surrogate model, and DAP toolbox is used as a rule book. It is like a rule book for all the things happening within the genetic algorithm. And scikit-learn is used for like the basic functions of like train test plate, mean squared error, R2 error, absolute. These are the things, right? So let's go this thing. So like and now going to the input. So like we have these material properties here, the Young's modulus, Ludwig material exponent, the pressure bounds. So like we will have these multiple pressure bounds across multiple target positions. So it will be like this 0 megapascal for the initial position of finger. Then we increase the pressure more as the finger is bending more, and the more bending of the finger, the more will be the pressure. These are the genetic algorithm hyperparameters, the population, the number of generations, tolerances, all of these things. These are the actuator and bone design parameters and their specific bounds. So we have defined these bounds in order to restrict the computation of the whole algorithm. These are the target configurations here. So like the MCP angle target configurations, the fingertip end positions. And here these are like across multiple poses. So like the 0 degree will be at the initial position of finger, and as we are progressing more, we are going towards the more bended position of finger. Here the Ludwig equation and PCC analytic equation has been defined. Design constants has been defined here, the validity things, and the volume calculations. Now these volume calculation will be further used for energy calculations. Now going towards the simulation stage. So here like this is the surrogate model training I am doing here using LHS sampling and using 5000 samples here, right? And this is the like the tune RBF thing. So like in the radial basis function, d theta is the main hyperparameter, and I am tuning it to get to get that at what value of d theta I am getting how much the accuracy of surrogate model in order to find the best value of d theta, right? So this is the thing. Here it is the DAP setup toolbox, which I said earlier is the rulebook thing. The GA individual. So we are creating individuals for actuator and for the bone. The G operator. So here is like the definition of crossover function and mutation functions within the actuator and bone. Evaluation functions. So here like this will be the definition of angle, the energy, all of these things. And this is the main optimization loop. So the main optimization loop is being divided into 4 stages: stage 1A, stage 2A, stage 1B, stage 2A, and stage 2B. And also I will like to talk about one key thing here is this warm start procedure. So like as I said that there are multiple target poses, and for each target pose I will be getting some specific design set, right? So like there will be an initial random population for the first pose, but the best population from the first pose will be acting like the initial population for second pose, and this will be happening for all the subsequent poses. So this creates a connectivity between all the poses. Here like this is the GA running here, and so like due to the time constant I will quickly shift to the result summary here. So like here you can see the pose 1 and the angle error, tip error, and now this specific design set will be acting like the initial population for second pose, and this is what I call the warm start procedure within the GA, right? So here like we are seeing this pose 9, right? And this will be our final pose, and this is the actual design set I will be using for CAD, right? Visualization thing here. So like here you can see the angle error across multiple poses, the tip position across all poses, the trajectory comparison. So like this blue trajectory here is being calculated by the end tip position across all poses compared with this orange trajectory, the target configuration I have given earlier. Also, you can find here the comparison. So this blue line trip trajectory has been now created specifically for that final design pose, the final design set I get, which I will be using for CAD, and compared with the target configuration. So talking about CAD models, let's go towards them. So these are the CAD model I have created by using the output from that code, and also I assembled them into a 4-fingered hand. I tried to simulate them in ANSYS using the nonlinear simulation, and these are the simulations you can see here. In the hand, I have experimented with applying different pressure for each finger. So yeah, this is the stuff I have, and I hope you like this video. Thank you.